Can you guys see my screen?
Okay. Hello and welcome, everyone. Thank you all for joining us today. My name is Karel Marin, and I'll be your host. I'm delighted to introduce you to Carlos Bengaly from Rio de Janeiro National Observatory. To tell you some background about Carlos, they did their undergraduate studies at Rio de Janeiro Federal University. Then they obtained their master's and PhD at Rio de Janeiro National Observatory. They also held a postdoc position at the University of the Western Cape and at the University of Geneva. And now they're doing a postdoc at the Rio de Janeiro National Observatory. Their research line is mostly focused on proving the standard model of cosmology and its fundamental hypothesis with current observations and forecasts using model-independent approaches. They're also interested in topics such as philosophy of cosmology, science communication, as well as LGBTQIAP+ diversity in the Brazilian STEM academic community. Today, they are presenting about proving the standard model of cosmology and its fundamental hypothesis, state of art, and forecasts. So thank you, Carlos, for accepting our invitation, and please feel free to start your talk whenever you're ready.
Okay, so good afternoon, everybody. So, well, as Gabriel just said, so I'm Carlos Bengaly, a postdoc at National Observatory in Rio, Brazil. So I'm gonna present I'm gonna talk about my research here. I mean, the things I've been doing like lately. And also I'm very grateful for the opportunity to give a talk here. I'm not sure if most people know that I was actually supposed to be working with you guys if there wasn't pandemics in 2020. So I'm not sure if Domenico ever or has told you guys about this. So I got a postdoc at your department. I was supposed to start in early 2020, but because of pandemics, I could not go. So I'm so excited to stay here in Brazil, which was easier. I could start anytime. I didn't need to go through bureaucracy of immigration and all this stuff. So, okay, let's start. Let's see. Okay, so this is the outline of my talk. I'm gonna give you a brief overview of the standard model of cosmology. I'm gonna make a question like, okay, we have a standard model of cosmology, but do we really understand the universe, the cosmos? And then I'm gonna present my research, focus on observational tests of the foundations of the standard model. Firstly, about testing of the observational tests of the cosmological principle, then about some node tests of the standard model and some other stuff I've done. And in the end, some concluding remarks and perspectives. Okay, this is the standard model of cosmology today. So just before I move on, you guys can hear me well, right?
Yes.
Okay, cool. So there might be some noise here, especially because of the airplanes, because I'm close to one of the airports here, so never mind. Okay, the standard model of cosmology, so can be synthesized as this pixel-like plot here, where different colors correspond to different components of the universe. In yellow, you have ordinary matter, and by ordinary matter, I mean matter made of baryons, like protons, electrons, and neutrons, like hydrogen and things that we know. And as you can see, it only comprises 5% of the universe, whereas dark matter corresponds to roughly 27% of the whole material and energetic content of the universe, and dark energy is about 68%. We know dark matter indirectly, we cannot see it, but we can detect it indirectly in galaxy rotation curves and the large scale structure. It is responsible for the formation of the structures of the universe. We know it interacts gravitationally with matter, but we still don't know what it's made of. And as for dark energy, we know that it's responsible for the late time cause acceleration. It's roughly 70% of the whole content of the material content of the universe, but we're still looking for, we still don't know its nature yet. So these quantities here were given by the latest Planck data release. Maybe I think it's 2015 and not 2018, but these numbers will not change that much. And the error bars for these quantities here are very small, so like roughly 1% or a few percent. So we have the question, what is dark matter and what is dark energy? But before I make this question again, I'm gonna say that this description here is the best we have today to explain cosmological observations, like the cosmic microwave background, the CMB. As you can see here, there's the temperature and isotopes of the CMB in millikelvin, in the scale of millikelvins, as well as the large scale structure of the universe. Here we have different colors correspond to different tracers. This is the latest map by this STSS collaboration. This spans the whole duration of the collaboration, so from 98 until 2019. And this is look back time, so roughly redshifts. And here also, maybe the first probe that gave us the evidence for lambda CDM and the standard model were the distance, luminosity distance to type 1a supernovae, which we understand that they are like standardizable candles. So if we know how bright they appear in the sky, we can also measure how distant they are from us. And we can use this distance measurements to test cosmological models. So this is the latest supernovae computation by Pantheon here, the Hubble diagram of this supernovae. But okay, what this lambda CDM model is really about? So this is like a non-extensive list of what these components are about. I'm not gonna go so much into details, but as for cold dark matter, this is like what we know so far. So it is needed to explain like the galaxy rotation curves and the formation of structures. We have some candidates for dark matter, but we still haven't detected yet any of them. And well, in the past, they used to think that maybe neutrinos, massive compact halo objects, or maybe some kind of modified gravity could explain dark matter, but looks like it's not the case. Neutrinos would have like different formation structure of the universe, different from what we see now. And as for machos, they would not really nowhere be able to take into account the amount of dark matter we see in the universe. As for dark energy, well, it's a kind of exotic component that behaves like a perfect fluid with a negative equation of state. It dominates the energy budget of the universe in the last couple of billion years. And why just now? The coincidence problem. The best candidate we have today is a cosmological constant, where the equation of state of dark energy is equal to -1, which is associated to the vacuum density energy. But then if you do so, we have a discrepancy with the predictions from the quantum field theory, like a huge discrepancy of more than 100 orders of magnitude. There are some alternatives out there, like quintessence, dynamic dark energy, some modified gravity models. I'm not gonna so much details. I'm just presenting like what's available in the literature. And well, this picture allows us to explain like what happens in the universe since the beginning, like not really the beginning, but since the inflationary period that happened 13.8 billion years ago up to now. There is also inflation. We explained the early universe. It solves some of the problems like horizon, curvature, homogeneity problems. But we still don't know exactly how to describe the very moments of the singularity that came just right before the moment of inflation. So this is still an open problem in cosmology. But okay, we have this model which is characterized by dark matter, cold dark matter, dark energy, and the early universe described by rapid inflationary periods. This explains very well the cosmological observations today, but to really understand what they're about. As I said, like we still don't know the nature of dark matter and dark energy. We know what they do, but we still know what they are. And still in the last few years, possible cracks in the standard model, like for example, the 8-knot tension, like the tension between the Hubble constant measured by the CMB and the supernovae, which are 4 sigma away from each other. And well, this is obtained in the very, this is obtained is still in the framework of lambda CGM. So it was not expected. The same thing for the sigma 8 tension, which is smaller than the 8 knot, but still out there. So this is a plot like of the 8 knot measurements that we have using CMB, using supernovae, calibrated by different CFIX and TRGBs, masers, and so on. And so we can compare the difference between them, between these results here. So given this scenario that we have a standard model, but we still don't know the nature of these components, and there are some possible cracks within this model. So one thing that we can do is like looking for alternative models and see if they can explain these tensions or explain the observations, as well as lambda CGM. But another route that I decided to take is to revisit the fundamental pillars in which the concordance model is based upon. So, okay, the foundations of the standard model, which is also a non-extensive list. We could say that general relativity is assumed to be the theory of gravity and the cosmological principle. Cosmological principle says that the universe is statistically homogeneous and isotropic at large scales. So the distance and ages in the universe are measured using the FLW metric, Friedman metric, Walker metric. And in a more simple language, you could say that we have no preferred directions and positions in the universe, from at least in large scales, roughly 100 megaparsecs. I'm going to show you some recent results on trying to establish this scale in which the universe becomes homogeneous. But then, okay, this description simplifies our lives quite a lot in terms of calculations. But then we can make the question, does the cosmological principle really describe the observed universe, or is it just a sort of mathematical simplification? So, because if you don't have cosmological principle, like if you do like a direct test of the cosmological principle and see that it doesn't explain the observations, we'd have to reformulate the standard model of cosmology from the very beginning. So that's the importance of, like focusing on testing such fundamental hypotheses. So this is the part one of my talk, in which I'm going to focus on testing cosmological principles, cosmological observations. So this is a cartoon in which I show, for example, the left hand side here, we have like, suppose that here we are in the center and make observations of the universe here in different, each shell would correspond maybe to a different redshift range. And here you can see that this inner shell, you can see like distribution of galaxies or stars or whatever, like around us. And you can see that they seem to be uniformly distributed across the sky. However, if you go to the outer shell, you can also see that it looks roughly homogeneous, like in every direction, like you can see more or less the same amount of objects. However, this outer shell is much less dense than the inner shell. So this universe would be isotropic, looks pretty much the same in all directions, but inhomogeneous, because I have a different density here in the outer shell. The other cartoon is the opposite. You have a similar density of airplanes here in the outer shells. However, they are all pointing to the same direction. So this universe would be anisotropic but homogeneous. It does have a preferred direction, but like you have the same density of objects in different ranges. And okay, the question is like, how can we test the cosmological principle? Or if we can test it directly. So testing isotropy is straightforward. We just need one observer like ourselves, and we are going to assume that we are considered like fundamental observers, which means that we have, by a fundamental observer, it means that the only sort of anisotropy that we would see is due to a peculiar motion. relative to the distance sources in other redshift ranges. And no other source of fundamental anisotropy besides this one. So we just need a fundamental observer and perform statistics across the entire sky to test its properties and to see if it's isotropic or not. But testing homogeneity is not straightforward, unfortunately. And this is a more technical detail, but the point is like we perform observations down the past light cone. And we do not do this on time constant hypersurfaces. We can still perform some consistency tests, like there is some consistency relation of the FLRW metric as proposed by these authors here in 2008. We can also determine or try to measure a scale of homogeneity in source counts using fractal dimension. So it's the fractality of the spatial distribution of galaxies, quasars, whatever. I'm gonna talk a bit more about this later on. But these are still consistency tests. These are not really direct tests of homogeneity. So I'm gonna show you a picture which is gonna explain a bit, it's gonna illustrate what I just said. So here we have our world line here. This is us. And these are the galaxy world lines. So we are performing observations here in a surface of constant time, which, okay, you could think of, we are making observations of galaxies in a specific redshift, say redshift 0.5. The point is like, we can only observe what's on our past light cone. What's outside the cone, we do not have access because the light hadn't reached us yet. Well, maybe it never will. So this would be a sphere of constant time, and we don't have access to what's outside the cone. So we can never tell what's going on there. But we can still, as I said, perform some consistency tests, which are important, at least for a sanity check. But this is the difficulty of testing homogeneity. Isotropy, however, it's much more straightforward. So, what are we to probe isotropy? We can use the counts of cosmic objects across the sky. Radio sources could be one of the main objects that we can use for this purpose, because they're very powerful traces of the last phase structure, and they can be observed at very high redshifts because they're very bright. And so the goal is to test consistency between the same B dipole, temperature dipole, which is assumed to be due to a motion, like a kinematic dipole, not a cosmological one, and test consistency between the same B dipole with the dipole we see in the radio source counts across the sky. If you find some inconsistencies, it may lead to a departure of the cosmological principle. So they should be the same if the same dipole is really due to a motion. We should see a similar signal in this angular distribution of radio sources. Otherwise, there might be something going on. So this is a set of works that we've done on this line. I've done these works when I was in my first postdoc in South Africa. So I'm gonna focus on the first two papers here. Okay, there are some other papers also testing isotropy with other traces, like using low Z galaxy counts in infrared, galaxy clusters, supernovae, GRBs. Okay, this is the first work on the dipole anisotropy of radio counts. So the question is like, is the universe isotropic? So we can see this figure here. This is the dipole anisotropy of the same B. This is well known actually since the late 60s, actually just after they discovered the same B signal, like Penzas and Wilson discovered the same B signal. Not much after this, maybe a couple of years after, they also found a dipole in this signal of the same B temperature. And this dipole is assumed to be a motion relative to the same B, relative motion to the same B. So I'm sorry here, it didn't appear the directions of the sky. So they found that this dipole due to a motion would be consist to a peculiar velocity of around 370 kilometers per second towards the direction of the Leo constellation. And on the opposite direction, you have Aquarius. So the point, like, if you can see the same dipole in the number counts of radio sources. This idea was originally proposed by Ellis and Baldwin in 1984. They developed all the formalism in which we can perform this test. As I said, like, if there's difference between the same dipole and dipole of radio count, this cosmological principle would not be valid unless there are system masks in the data. Okay, so I'm sorry that some equations here are not appearing. So anyway, but this is still good for now. So if you go to the paper, they explain, well, how can you test cosmology? How can you measure the dipole dual motion, relative motion in the radio sources? We basically need two ingredients: the spectral index, which relates the flux of the radio sources with the frequency we observe them, and the number of radio sources above a certain flux threshold with respect to the flux. They assume to be power laws, and this assumption holds well. And we perform a Doppler boost in the frequencies and the aberration of angles here in the number of sources. Here it's n, but it's actually a count in solid angles. So the angles are aberrated due to each motion. And so there is a relation here which is not appearing. I'm sorry, can I maybe try to use another PDF? Can I just like unshare and maybe show like in another PDF program, because maybe
yes.
the questions will appear.
Yes, go ahead.
I'm sorry. Yes. Like I didn't know it was gonna happen. It didn't happen before. I'm really sorry. Just a second.
Go ahead.
The same problem is happening here with this editor. But anyway. Anyway, so I can show you then afterwards, like the relation between the number of observed sources in a given direction with respect to our motion relative to them. So it also relates the alpha, x, and the velocity that we're moving relative to the sources. So this comes in the form of a dipole, which has an amplitude, which is related to these quantities here, and the velocity that we're moving, and also the angle, the direction that we're moving towards to. Don't know why it's not moving. Okay, here it goes. So typical values for the dipole amplitude. So typical values for alpha and x are around 0.676 for alpha and 1 for x. And beta, assuming the same velocity as we can see the same b, this would be beta v over c, which is 0.00123. And then we'd have the typical dipole amplitude to be around 0.0046. So try to keep this number in mind, because we're trying to see if we can really, like, say, if it's consistent with observations. Okay, so I'm going to talk about how we actually done the test. So how did we construct our observational sample to perform this analysis? So this is going to be a bit more technical. I'm not going to so much into details. But we use two largest radio catalogs available today, NVCS and TGSS. They probe a good amount of the sky. So all the declinations are above 40 degrees for NVCS and above 53 degrees for TGSS. This is the flux threshold we selected. So they are different because they're operating different frequencies, but then we can relate these fluxes, like convert the fluxes to each number by doing this. I'm not sure if somebody raised their hand.
Yes, so
Yes,
we have a question. Go ahead, Daniela.
I have a question.
Go ahead,
Sorry.
please.
Well, I don't know about this, but is there any correction to these sources, for example, from some from the galactic plane or something like that that can contribute to the dipole? Or what are the corrections you have to make to these sources? I don't know if the Milky Way radiates in this spectrum. Yeah.
So yeah, this is a very good question. So in this case, I'm going to talk a bit further about this. In the data, there are no corrections there are no specific corrections like in the raw data, but we've done some further, some further corrections and some further cleaning of the data in order to avoid, let's say, local contaminants of the galaxy. I'm gonna just show you the next slide, perhaps. Yes, exactly. So we further cleaned the catalogs, like we removed some regions in which we had like large MIS noise in some specific pixels. For the case of the GSS sample, we also eliminated the galactic plane in the lowest latitudes, and also we also eliminated some pixels that were like close to 1 degree of local radio source local clusters, which could also bias our analysis. And also further on, we also eliminated some regions whose galactic foreground emission was very high. So at least we try to do this is what we try to do to avoid, let's say, spurious contamination, especially the local ones. Did it answer your question? Okay, thanks. Okay, so for the data analysis, we use the hemispherical comparison estimator. So we look for the number of sources in different hemispheres in a way that the direction in which we find, let's say, the maximum frequency asymmetry between hemispheres would naturally give us the dipole. So in order to do this, we made like source count maps using helpits, and we compared the real data with some mock realizations. In order to produce these mocks, we produce a power spectrum from CAMP sources, and we plug the power spectrum into another code called Flask. It's a very nice code written by a former postdoc here in São Paulo, in which it produces, like from a given power spectrum and from the survey specifications, it produces mock catalogs, assuming that the density fields of the number density of galaxies follow a log normal distribution. So this is not like N-body or like QPM code. It's more simple, but it's very functional at least for large scales. We got something that I have to say about this catalog is that they don't have shift of the sources. So in order to produce a fiducial power spectrum, we need to have let's say, an unexpected distribution of sources across the redshift ranges. And we got this number, an estimate from a big simulation from S-Cube that was produced like many years ago. There is a new one, but it wasn't available when we did this paper. And also the bias, also the bias of these radio sources. So we got this, we use this fit here, following these authors here, Nusse Tiwari. And we also verified if the flux density errors of flux calibration can affect the dipole measurements. So these are the number count maps for each survey, LFSS on the left and TGSS on the right. So the numbers here are negative because it's a density contrast. So that's why it's negative. As you can see here, gray, we have the massive regions in the sky. So this part here, here is the part that we don't have observations. These are the lowest declinations in which NFSS and TGSS could not observe because of the positions on Earth in the northern hemisphere. And this is the galactic plane that we have eliminated, as well as some regions with high foreground contamination from the Milky Way. So, okay, these are the results we got for the dipole using this hemispherical comparison estimator. Again, NFSS on the left and TGSS on the right. And, well, if you can remember well the same B dipole that I showed you a while ago, by eye, you can see that the directions are not so far away from the same B dipole, the directions we got from both catalogs. However, if you also remember some slides ago, the expected dipole amplitude, if it's consistent with the same B, would be around 0.0046. However, we got 0.23 for NFSS and 0.70 for TGSS. So this is like 5 times larger, and this is 12 times larger. And the direction is pretty much consistent. So this is quite puzzling, to say the least. These are our results comparing to others in the literature, at least back in 2018 when we published this paper. So there are some new analyses, but all of them, they are consistent with the values we got. And our values are also consistent with all the NFSS analysis. In TGSS, we're the first ones to test this catalog to see the dipole, but other people have done the same, and they also found consistent results with ours. And this is the results for the mock data performance. So we produce 1,000 realizations using that prescription, like producing the power spectrum using CAMB, assuming lambda CGM, and that specification that I told about this redshift distribution of sources, the bias, and so on. And so we produce like mock catalogs, 1,000 mock catalogs, and this is the histogram that we obtained for the dipole from these mocks here, in black for TSS and in red for NFSS. And as we can see here, only very few realizations can provide a dipole as large as NFSS, and nowhere close to TGSS. So our results are quite discrepant, like with the expectations, like the theoretical expectations. Like we cannot really produce such, it's very hard to produce such large dipole amplitude like at random. These are the same mocks, but we have included some flux calibration. We have included like a toy model for the flux calibration. Flux calibration can be, let's say, declination dependent. It's something that has to do with the telescope configuration. And as you can see here, even when we include this flux calibration correction, we cannot still, let's say, obtain such a large dipole at random. So it's a quite puzzling results. And well, at thus far, we still do not have an answer, but we can say at least that these catalogs are still very, very limited. So for now, we have to wait for the next generation of radio catalogs to perform this test again and see what happens. But for now, we can still test something. What happens in smaller angular scales? So this is a work I've done with 2 former master students in South Africa, Nandi and Albert. So these 2 were I co-supervised both of them. So this was pretty much the summary of the work of the master's thesis. We used the NFSS sample, again, the same mask the same way that we eliminated spurious contaminations that we've done before. But instead of looking for the dipole, we're going to look for statistical isotropy tests. So in this case, we drew patches in the sky of different degree size, and you can put the variance of the source counts inside these patches. We eliminated some patches that had many, let's say, masked pixels, because it could contaminate on it could give us some spurious results. And we used ANOVA to compare the variance between patches and the variance within patches. In this case, this test is built such that we've got one, we have isotropy. Otherwise, we don't. So it's a sort of local variance test that we compare the variance of data versus the variance of the mocks, similar to what these authors have done. Akami used SAMB and Alonso used a low-Z galaxy catalog, but they performed the same analysis, a similar analysis. And these are the results we got. So here, From left to right, you have different rejection criterion for the pixels to be eliminated within patches. So here we eliminated every patch that had at least 10% of the pixels masked. Here, 30%, and here, 50%. And from top to bottom, we have like patch size of 15, 20, 25, and 30 degree size. You can see the histogram of the mocks, and the vertical lines correspond to, the vertical red line corresponds to the real data, whereas the magenta lines here correspond to the percentiles of the histogram. And as I can see, in all cases, the red line here is well within these boundaries of this 95% percentile boundaries of the mocks, which says that at least up to 30 degree size, the NVSS map is quite isotropic, statistically isotropic. These are the amounts, these are the maps, sorry, you got for each degree patch size and for each rejection criterion. Okay, so these conclusions with regards to testing isotropy with radio sources. We can see we found no evidence against statistical isotropy in the source counts, in the source counts, at least in scales smaller than 30 degrees. The dipole, however, anomalous, which was confirmed in later analysis. However, TGSS counts, according to other authors, they are anomalous even at 10 degree size angular scales, which seems to be due to the flux calibration, which is harder to do, at least in the low frequencies, low radio frequencies which TGSS operates. So it's a quite of a challenge. They also found a similar dipole anisotropy in AGNs. Most of the sources are also AGNs, but also some people use infrared, like infrared observed in AGNs observed in infrared, and they found the results. So we have to wait for the next generation servers like SKA, EMU, which is a pathfinder of SKA, and also LOFA, which is already operating and giving these early data. And so we've also done some tests of SKA to predict the cosmic dipole, and you can see that the constraint is going to improve massively from what we have now, which I'm not going to so much further into details. So let's focus now on the scale of cosmic homogeneity with quasars observed by Sloan. So this paper was published early this year. What's the idea behind the test? As I said, homogeneity cannot be tested directly, but we can perform consistency tests. A practical way to do it is to compute the fractal dimension of the spatial distribution of cosmic objects. This was originally proposed by Petronero, 1987. So there is a very nice review on this topic by Coleman and Petronero in 92, it's a physical reports. And we expect that the fractal dimension would approach 3 when and if the universe is statistically homogeneous, which means that it would be indistinguishable from a random distribution up to Poisson noise. In small scales, we know the universe is very lumpy, so we expect like this fractal dimension should be smaller than 3, but we expect it to approach 3 up to some scale if the universe is truly described by cosmological principle. In absence of this transition scale would hint at the same of cosmological principle breakdown. So this is the original paper by Petronero. So this is the method in data analysis. There are a lot of things going on here. Just for you guys to know, we use the latest release of SDSS quasars. We bring the data into two redshift ranges between 2.2 and 2.4 and 2.5 to 3.2 in order to have at least roughly 20,000 objects. I mean, we've done some tests, and like if you have less, like say less than 20,000 objects, so the analysis is noisier. So that's why we chose this binning. And we compute the integral correlation fractal dimension like this. So here we have the integral correlation, which is related to the 2-point correlation function of the data and compared to the random. And D2, like the fractal dimension, would be related to the integral correlation like this. the log derivative. And we compare the results we got from the real data with the theoretical predictions. We compute the actual two-point correlation function from the meta-power spectrum as provided by Planck. And then we can compute also the integral correlation as well as the fractal dimension and compare the results we got. Note that we have to debias our analysis. So in nature, I mean, we have a catalog, the quasars, galaxies, they all have a bias, how they trace dark matter. So we have to take this into account, at least debias the results we got in order to, the observational results we got in order to compare with the theoretical prediction. Okay, so these are the results we got for the first bin. So in red, you have the observed results for the two. In green, the green line would be the theoretical prediction. And in blue, we have the bias corrected or the biased results. So like when we debias the red curve here, that's what we got. And you can see it's very consistent with the theoretical predictions. The same happens for the other red bin in a deeper redshift range. And here we compare the results we got for the scale of homogeneity, which, sorry, I didn't mention, but we consider the scale of homogeneity where D2 reaches 2.97. So 1% of 3. We can see it never really gets close to 3, never really, but gets very close to 2.97. So the scale where we have 2.97 is, okay? And we compare the results we got for these new results with previous ones using the previous data release of quasars in a, like say, lower redshift ranges. And this would be the theoretical prediction from CAMP. And you can see that it matches really well. So as you can see, we can see that there is an evidence for such transition scale of the homogeneous scale, which would be the scale at least where the feasible Robertson-Walker relation is valid. Okay, so I'm so not sure somebody raised their hand or there was something.
It's me, Domenico.
Okay.
If you go back to the previous plot. So as far as I understand, this is the fractal number, right? That you're plotting according to the size of the spheres. And so one question is, well, how to say, are you considering spheres that do not exceed, for instance, the volume of the survey, or?
We are.
Okay.
Yeah, we have to be careful with this because otherwise, like you would have, let's say, if we go, like say, outside the border of the survey, we do not have any counts because the survey is not observing there. So you would have, like I say, an artificially smaller scale of homogeneity, but this would be a spurious analysis. So we're careful, like, to do this, to avoid this kind of issue.
Because I wanted to ask, I'm asking this because I was reading the paper, the Alonso et al., where they do this stuff, basically. And they show a similar, well, it's not a similar, actually, I think it's more evident, of a bias on the fractal number, especially a high radius. And so I was wondering, I mean, Alonso et al. Discussed about the spheres of the they used to take, but I think they minimize the problem. So this is the reason why they have this bias on especially a high radius. So that's why I was asking to you.
Yeah. We have to be careful with this. I mean, maybe if you do like the same, if you do the same, like say, if you do not correct in everywhere around the survey, maybe it kind of compensates. Maybe the effects cancel each other, but we're careful actually when we get like large sphere radio, like for example 200 megaparsecs of size. We try to be careful like just to see whether it's going outside the border of the survey.
Whereas at lower radius, so there's a lack because basically you don't have any sources, or if you have few sources, or is there something else up there?
Maybe because of the number of sources are quite few, like in smaller regions, so we don't get many sources.
Okay, I see. Okay. Okay, thanks.
Sure. So this would be the part 2 of my talk. It's going to be a bit faster. I'm going to I'm not going to so much to details, but these are about new tests of the standard model using both available and future observations. So the first work we've done is the so-called OM diagnostic, a new test for the flat lambda CGM model that was published early this year as well. So the main idea in this case, we simulated H of Z, like Hubble parameter measurements of next generation surveys, like Euclid, DESI, and SK intensity mapping. That we expect that they're going to provide like very good measurements of H of Z with a few percent uncertainties. So we follow the next, when I say that we follow the specs of the surveys, which means that we got the redshift range that we expect, that they expect to make observations. And as well, they also have a prediction for the error of H of Z in each redshift range. So we took this into account to produce the simulations. So the node test of the flat lambda CGM model, it was originally proposed, I think, like 15 years ago, which is a consistency relation following this. So following this OM test. OM should be equal to omega m if the universe is really described by flat lambda CGM model. Otherwise, if you have any deviation, this would be a smoking gun that we have something else. There is also this LM test, which is the same as OM, but in this case, it's just the derivative of the test with respect to Z. So LM test is a bit easier. It's a stronger test because we can compare, like we have 0 for flat lambda CGM and non-zero for other models. It's easier like to know, it's easier than in this case here, where we have omega m, in which we can measure omega m with many observations. We still never know like the true value of omega m. We just have like we can just make measurements and that's it. However, this LM test, we need to compute the derivative of E of Z. So this makes the test a bit harder because we have some smacking effect because of these derivatives here. And in order to, from the data points we simulated here for this surveys, we reconstructed the curve along these data points using a non-parametric method, Gaussian processes, as available in this code called GAP, which is available here. So I did not write the code, like it was my inner cycle, like almost 10 years ago. But since the code, the original link is broken, so I re-uploaded in my GitHub for those interested. And we also simulated some other cosmological models, not flat lambda CGM, to see how they differ from each other. These are the results we got for OM on the left hand, on the left blocks, and LM on the right. So in the top we have Euclid-like survey, in the bottom we have SK-like survey. And these are 5 sigma error bars for OM, for this OM test, and 3 sigma error bars for LM. And especially for the case of SKA, we can see that here in red you have the simulations assuming lambda CGM. As you can see, they're just like around the omega m line. And in other surveys, they do deviate from omega, especially in lower redshifts. And as you can see here, like we can see that we can tell them apart very well at 5 sigma using SK specs. And in the case for LM, we have some overlap, especially in the lower, in the higher redshift ranges. As I said, this LM test is quite more degraded because we need to compute the derivative of H of Z. But still we have 3 sigma, we have a 3 sigma, let's say, we can still distinguish between them at least in 2 sigma in most of the cases. Maybe not between, we cannot do this for lambda CGM and K lambda CGM, which is a curved lambda CGM model, like a lambda CGM model which has some curvature. But from at least the dark energy models like CPL, both CPL models we chose, we can tell them apart very well, even with such tests. This plot is the same as before, but assuming more optimistic uncertainties for Euclid and SKA, to see how well can improve these results, and we can improve marginally if we reduce the uncertainties by 30%. Okay, so this is a paper which is still in preparation. Okay.
Carlos, may I ask you a question on the previous plot?
Sure.
So how many, well, let's say data points do you have for SKA?
We have around 30 data points, if I can remember well. 30 data points for SKA, maybe 20 for Euclid.
Okay, because I'm surprised about the errors between the OM test and the, as you said, LM test, which, okay, the second one has derivatives, no? So if by eye at least, I can see that they're more or less the same.
Yeah.
Kind of.
Yeah.
So I'm surprised about the small errors. So that's why I asked, because in Euclid you can see a difference clearly.
Yeah.
No? And but in SKA, no. So do you have a fast answer for that?
So the number of data points, it should be around 20 or 30 data points. I do have to check the paper again.
Okay.
We assume that it was somewhere around 20 or 30 data points each.
Okay, but usually derivatives, give a lot of errors on the final test.
Yeah.
Okay,
yeah. So that's the disadvantage of the test. It's more robust because you just need to compare to 0, which is a number that we know well. But then computing the derivatives there degrades a lot. Like even when you have very good measurements of h of z as we expect to have, when you make derivatives or integration, so the errors just like blow up.
Yes, exactly.
Yeah, but the number of data points on the top of my mind, I have forgotten. But after I finish, I can look for it. Okay.
Anyway, thanks.
Okay. Welcome. So this delta diagnostic is a new test for causal acceleration. These results are still preliminary, so it's still like an ongoing project. So we used a new test based on the idea of a cycle in Schwartz 2008. In which the null hypothesis is that the universe has never accelerated. So we have the log of E of Z would be like the integral of 1 plus Q, the acceleration parameter, with respect to Z, like this. And if the universe has never accelerated, we would have Q equal to 0, at least bigger, at least larger or equal to 0. And then we have E of Z to be 1 plus Z, like a universe that is at least bigger than this value if the universe never accelerated. And so the radial co-moving distance would be given by this expression here, if the universe has never accelerated. This delta diagnostic is such that we compare, like say, any observable that you have, like angular diameter distance, GL, H of Z, whatever, the difference between this quantity we are observing minus the value of the quantity for a non-accelerating universe. They should be at least bigger or equal to 0 if the universe has accelerated at some moment. So we use supernovae and the transversal and distance and the measurements for the transversal mode of BAO, which gives us the angular diameter distance measurements. And we use this instead of the, let's say, 3-dimensional BAO, because the angular BAO, we can obtain this with minimal assumptions about the underlying cosmological model, which is not the case for the 3-dimensional BAO. So, and we also perform this Gaussian process reconstruction on this data. And these are the results we got. So 0 would be the line that says that the universe has never accelerated. These are the results for the BAO data. And as you can see here, these are 1, 3, and 5 sigma error bars up to redshift 1.2, 0.3. We can see that there is a clear evidence that at least in 5 sigma we have like evidence for causal acceleration using this test. Note that in this case, just like the other case, we make no assumptions about dark energy. Like we just doing like no test. So just to see if you have London CTM or if you have cause acceleration or not. And these are the results for the supernovae data, which tells pretty much the same result, as we got for the BAO. And okay, miscellaneous stuff I've been doing. This is a very final part of the talk, so that you also found how well can SK and Euclid probe 8 knot and Q knot, that the acceleration parameter today. We can measure 8 knot to almost percent level precision, and also using Gaussian process. So we made no assumption about dark energy and still be able to measure 8 knot with very good precision using the surveys. This would help us at least shedding some light on the 8 knot tension. And probe acceleration at least with 5 or 7 sigma confidence level, all in a model independent way. We also found no evidence for a hotter universe that could solve cosmological tensions as was proposed last year using T of segments from clusters, and no evidence for supernovae absolute magnitude evolution, which was a collaboration that I've done with Domenico last year. Some measurements of the angular scale. We're also doing some measurements for the scale of homogeneity, but the angular scale of homogeneity, as proposed by Alonso 2014. So this angular scale of homogeneity, analogously to the case of angular BAO, we do not need to convert redshift into distances to make our calculations and to get the 2-point correlation function. So in this case, the angular scale of homogeneity would be more model dependent, yet more noisier than the measurements I just showed you. We're doing this analysis now using the luminous red galaxies by the latest release by STSS. It's in preparation, and also measuring the speed of light with some, we're also making a cosmological measurement of the speed of light. We got roughly 10% of precision using supernovae and cosmic chronometers. So it's a work in preparation by a master student I've been supervising, Gabriel. And well, as for concluding remarks and perspectives, we can say that, well, as for cosmic isotropy, to test with radio sources, well, they provide a dipole larger than we expect. And so, but the direction is quite right. It's quite consistent. It's still a puzzle, but we're waiting for next generation data for radio surveys to see what happens. We can also see that the quasars of the latest slow give us a characteristic scale of cosmic homogeneity, which is agreement with the cosmological principle and the fundamental hypothesis behind the standard model. And future surveys like Euclid and SK can perform new tests of the standard model and measure cosmological parameters with very good precision, with no assumption on dark energy a priori. And well, this is the take-home message that we are living a very exciting transformational era in cosmology. And we cannot, and besides probing cosmological parameters and test cosmological models with, let's say, unprecedented precision, we can also test the fundamental assumptions underlying the standard model with very good precision. And well, that's it. Sorry if I took a bit long, but yeah.
It's good on time.
Thanks, guys.
Thank you, Carlos, for your nice talk. I think we have some time for questions. So if anyone has one, please go ahead.
I have a question mostly related to your last point. Okay, it's a paper in preparation, so probably you cannot say much. But I mean, how?
Sorry, which one? About the conclusions.
Yes.
Okay.
The speed of light. How do you measure that? Okay. The standard chronometers. I mean, I always thought the standard chronometer we have to assume the speed of light, you know?
I mean, the speed of light is out there when we get the data. Like, for example, when we get the data from supernovae, we have to assume like a speed of light or use some Newton constant to measure the luminosities. There is a method proposed by Vincenzo Salzano in 2014 with Ruth Laskos and some other authors in which it says that, for example, if you can measure the angular diameter distance, so it is expected the standard model to have a maximum, like some redshifts. And then in the case, so at this maximum, the derivative of dA would be 0, and then we can just measure C to be dA times H, the Hubble parameter at this redshift, where the angular diameter distance is maximum. So we can measure the speed of light there in this redshift. There are other ways to do some, so it's a very clever way to do it. So the main point is like, okay, whether we have good enough data to do this. So angular diameter distance, that's what they proposed. But the data we have now for angular diameter distance is not so good to reach such redshift ranges. So we converted the luminosity distance from supernovae into angular diameter distance using the distance duality relation. That's why. So.
Okay, I see now.
So and we got a result which is consistent with the laboratory measurements, but much bigger error, like around 10% of the error. But like given that it's a cosmological measurement, it's competitive to what has been done like lately.
Okay. But since the peak of
as far as no, go ahead. Sorry.
So since the peak of the angular diameter distance depends on cosmology, do you have? I'm asking, I'm just ignorant.
Yeah.
Do you have some degeneracy? So I mean, with the
parameters? In our case, in order to avoid this issue, we also did like a Gaussian process reconstruction. So at least we got the reconstruction directly from the data. We did not assume any model. However, it's true that there is some degeneracy, especially with the cosmic curvature.
Okay.
This relation, like I told you, only holds for a flat universe. If you have a curvature, you have degeneracy between a curvature and the time varying speed of light. And this degeneracy is very hard to disentangle. Salzano also did some analysis focus on this, and he found that, as far as I can remember, he found that for the curvature to make a difference, we'd need to have a very, very small, let's say curvature is degenerated, but very, very mildly. So could be the case for next generation surveys in which we can measure curvature very well. This could be the case, but not for the case of current data. So we do not need to worry for now with this degeneracy.
Okay, yes. Makes sense. Thanks.
Sure.
Any more questions? Okay, if there are no more questions, I think we're good on time. So thank you again, Carlos, and thank you everyone for coming today. Have a great day.
Thanks a lot, guys.
And hope to see you again in the next seminar. So, bye.
Okay, guys. Bye-bye. Cheers.
Thank you, Carlos. Ciao.
Thanks. Ciao.
Ciao, ciao.